Oh, great. Okay.
Because every once in a while you come on my 40 page on YouTube.
That's awesome. Every exponential function can be rewritten as a logarithmic function, and every logarithmic function can be rewritten as an exponential function. There are some parallels here. The base of my exponential function is the base of my logarithm. The answer to my exponential function is what I take the logarithm of, and then what the log is equal to is the exponent in my exponential function. So what we're going to start doing is we're going to start rewriting these as logarithms and as exponentials so you get kind of used to it. Just know that this is how they relate to each other. So the bases match. We take the logarithm of the answer and set it equal to the exponent. On your calculator, you may notice you have a log button. We are not using that right now. Okay, because it is very limited and we're going to be working with logarithms that don't fit into what your calculator wants them to fit into. So we're going to start just by changing back and forth between logarithms and exponential functions and then seeing how their answers relate. The first one that we are rewriting is log base 2 of 8 equals 3. Make sure your base is set below where your 8 is. We should be able to tell the difference between a sub 2 and a 2 or number that exists here. The sub 2 is your base. Okay, make sure you can tell the difference in your handwriting. So if I were to rewrite this as an exponential problem, what is the base of my exponent?
2.
2, because that's also the base of my logarithm. What exponent am I using here? 3. It's what my logarithm's equal to. And then that tells me that my answer is the big number in the logarithm itself. So log base 2 of 8 equals 3 is the same as 2 cubed equals 8.
Oh, interesting.
That's fine.
Do we kind of see how all of those numbers moved when we rewrote this from a logarithm to an exponential? Do we all kind of see that? Of course, we're going to do another one because it's nothing if we don't practice it.
Where did the log go?
It disappeared. So logarithm is just another way of re-representing that information in a different format. So when we change formats, it disappears. Example B. Log base 4 of 1 equals 0. On your own, try rewriting that as an exponential problem.
Oh my God, wait, I just realized that they're accurate. Hi, what's up? Why?
We're gonna play it.
I think it's in that closet.
Okay, so who would like to be confident in their answer and tell me how you did it? I want a boy. I would like a gentleman from the class to tell me. Shadow, you don't count.
You're in the wrong class.
Shane, awesome.
I'm not really sure why I did, but I know there's a 4 on the other side.
Where does the 4 go on the other side? Is it the answer, the exponent, or the base?
I'm just gonna write it.
Okay, that works.
Not with your husband.
It's coming on the right. I put the 4 right here.
Okay, then what?
I'm not sure after that. I didn't get that.
Yeah, we play Guitar Hero 7th hour because they can't do anything in class because I step. Well, when we have nothing to do in class, we'll think about it. Okay, Shane's asking a question. Ask your class.
Where does the 0 go?
It is the exponent on the 4, which means that the 1 is the answer to my exponential problem. So it should go on that side.
Yep.
Write the 1 on the right side of the equal sign. There you go.
But that is equal.
Does 4 to the 0 equal 1?
Yes.
Oh, let me ask that again. Does 4 to the 0 power equal 1?
Yes.
Yes. Anything to the 0 power equals 1. Anything at all. It doesn't matter if it's a 4, it doesn't matter if it's an X, it doesn't matter if it's an E. anything to the 0 power equals 1. That should be in your brains somewhere. Thank you, Shane. You can go sit down.
It wouldn't help that equals right there. I thought that was part of the problem.
Oh, yeah, no. Different colors means different problems.
Oh my
God.
god. What is that?
We are not asking.
What that's supposed to be a 1.
Okay, so there are, of course, some more examples if you wanted to look at different conversions from logarithmic to exponential, but we don't need to go over those. We will go over 2 that you should have in your brain, and one is the 0 exponent. So these are just some properties. If I have log base b of b equals 1, as an exponential, that is b to the 1 equals b, which just highlights that anytime I take a base to an exponent of 1, that means it exists one time in my problem, so it also has to be the answer. So anything to the 1 power is just itself. The same thing applies if I take it to the 0 power, which we already highlighted. Anything to the 0 power equals 1. So those are just some properties you should definitely have written down somewhere on your notes because they're very, very helpful.
I didn't know you could have 0.
Yep, always. We can have negative exponents, we can have positive exponents, we can have fractional exponents. There is no limitation. So as a reminder, negative exponents will also occur in this.
Can you have pi as an exponent?
Yeah, it's still just a number. You won't because it's super ugly, but you could.
Wait, so you can have like the actual simple pi.
Yeah, because it's a number. It stands for an irrational number. Yep. Okay. So what we're going to do now is we're going to use this conversion to actually solve some logarithmic problems. Can't be yawning, man. So this logarithmic problem is log base 4 of 64 equals x. How in the world could this be helpful? Or could rewriting this as an exponential be helpful in solving this problem? It'll look nicer. Okay, Cadence, what's it going to look like when I do that?
Slow. Okay. It'll be 4 to the power of x.
Yep.
Equals 64.
Awesome. How is that helpful for me?
You can solve it.
I can solve it. 4 to what power equals 64? Cubed. So you could do what we did last time, and we could recognize that that is the same as 4 cubed, which means that x has to equal 3. Because remember, if we get the same base, the base disappears, and I'm just dealing with the exponents. Same process. If you recognize that 4 cubed is 64, you don't need to show me this. It's okay to just answer that x equals 3. Are we okay with that? Everybody see how that was helpful? From here, without that, I would have had no idea what I was doing. But being able to rewrite it, let me see it from a new vantage point, which allowed me to solve it. So of course, we're going to do another one.
That's all we're doing?
No, there's graphing.
I don't think the graphing will be too long. So,
I didn't even have to graph the other stuff.
And we have decimals. And we have decimals. The first thing that I would probably like to do here is I would like to rewrite 0.2 as a fraction.
Yes, please.
1/5, good. So this is the same as log base 5 of 1/5 equals x. Keaton, what would I do next?
You do the 5 to the x equals 1/5.
How is that helpful for me? How can that possibly give me a solution?
You solved it.
Okay, so what exponent is going to take a base of 5 and turn it into a 1/5?
-1.
-1, how do you know that?
Because in negative.
So a negative moves a base from whatever side of the fraction it's on to the other side. So currently this 5 is in the numerator. To make it match 1/5, I had to move it to the denominator, which means x had to be -1 here. You also could have worked backwards and recognized that 1 over 5 is the same as 5 to the negative 1. My bases cancel, and I still end up with x equals negative 1. It is your choice how you choose to solve it. If you want to keep writing it out like we did last time, that's perfectly fine with me. Questions, concerns, or issues with that? Are we all okay? Do we understand how this helps us? So now we're going to go ahead and identify a couple very common logarithms that we'll come across, and then we will start graphing. So the most, I don't know, I hate to say common, but the most popular or mostly used type of log is called our common log. Common log is a log base 10. And it is also just written as log of x. So if you see log of some number and there's no base, that means it's a base 10. This is the number system that we count with, or that we deal with in everyday life, which is why it's called our common log, because it's the most widely used. So common log is base 10, or it could just be log of some number, which we assume just means it's base 10. The next one is called our natural log. This one is my favorite. And it is a log base E of some number, and this is always written as natural log of x. So anytime you see ln, that means natural log, which means logarithm base E. I always use a curly L for my natural log versus a straight L for my common log. It's okay. We're going to use this a lot, so you will get more comfortable with it. Just know that these are the most commonly used types of logarithms. So log base E and then log base 10.
How many logs are there?
An infinite number, because you can have a log of any base. But these are just the ones that we're going to use the most. Okay. So now we are going to get out your calculator, and you're just going to practice plugging in logarithms just to test it. Make sure you can push buttons in the correct order. So the first one I would like to find is log base 10 of 12. The first question I have for you is how many of your calculators have a button that says log base 10?
I don't know. Is that what the 10
Like
is?
log with a little 10 underneath, all on the same button. How many of yours has a button that has a log with a little 10 on it?
I got a log and then
Yeah.
Okay, none of them.
Oh, okay.
So what do I know this is equivalent to? Because as of right now, I don't have a part on my calculator that matches this. How can I rewrite something that has a log with a base 10? We just leave the 10 out. So this is the same as just log of 12, and I have just a log button on my calculator. So that's what I'm going to push, and then I'm going to type in 12, and I'm going to press enter.
1.07.
Good. That means you plugged it in correctly. Do we all see the nice little log button? That's how you plug that in. That only works for log base 10s. So of course, later on, I'm going to show you a really cool way to get around that on a calculator, because we don't always deal in base 10, but that is only a base 10 calculation, which is why calculators are limited. Anybody not get 1.079? So then what if I present to you a logarithm that looks like this?
There's some calculators that can't.
There are, yes, but majority of them are not. So now I have a log base E of 3. As before, I don't have a log base E button on my calculator. Do I? No. But what do I know log base E is equal to? ln, or natural log. So this is the same as natural log of 3, and I have an ln button on my calculator. So you're going to push that, and you're going to push 3, and you're going to press enter.
Oh,
Oh my
ln.
It's below, it's above the pi symbol below.
And then you get
Is it a secondary?
Oh,
No.
No, it should be there. Sometimes it is a secondary, so you should definitely look for that, but every calculator has log and it has natural log. So what does that equal?
I don't know what a lot of these.
That's okay. We will explore them, and some of them you will never use. So it should be approximately 1.0986. Anybody not get that? Everybody's okay with plugging a log base 10 and a log base E or natural log into your calculator? Yes, both.
How do you round? Because you rounded two different.
If I don't tell you, yeah, I'm just gonna say it. If I don't tell you, I went 4 decimal places because this is an honors class with the intention that you're going to continue on with honors level math. So I prefer 4 decimal places. 4 decimal places. Everybody, 4 decimal places. Okay, that is my status quo. Anybody not get this value? Are we all okay with plugging it into our calculator? Okay, I know you're all super bored now. So this is where it gets interesting. We have different types of logs, which means we have different types or different ways to solve them, which also means that we have different types of logarithmic inverses that also occur. So these are ways of actually canceling out a logarithm in an equation or an expression. These are very, very handy to us. I know. So these are our logarithmic inverses. The first one is if I'm taking the log of some exponential problem and the base of my exponent and the base of my logarithm match, they cancel each other out. So if these two values here match, then what's left in the exponent is the answer. Okay, so that is an inverse that occurs with logarithms. Another one that occurs is if I take the opposite of this and I take base b to a power of log base b of x, the same thing is happening. I have a base b and I have a base b, which means they cancel each other out, leaving just whatever I was taking the logarithm of. So these represent inverses of each other, or what happens when I get a base and a log that cancel. Another set of inverses, actually no, we'll just do examples from here. No, I lied, we're not. I'm gonna show you the other set. Because it never hurts to have them in the same place. So if I'm doing, no. If I have natural log of e to the x, I know that natural log and e are going to cancel because natural log is the same as log base e of e to the x, which is a prime example of how when the base of my logarithm and the base of my exponent are the same, they cancel, leaving just the x, or whatever variable or number is there. The same thing occurs if I have an exponential that has a base e raised to the power of the natural log. Again, that is the same as e to the power of log of e of x, where my base and my base are the same, so they cancel each other out. E and natural log are the most common inverses that we are going to use when it comes to logarithms. And they're going to play a very important part for the next 2 years. And it is. And this is the first time you're really looking at it. So I expect it to be confusing, which is why it's not on your homework. Yes.
Is the E the sum?
On this one?
No, the next one.
Yeah, E is my base on that. So it's the base of my exponent and the base of my logarithm.
So will this stuff be on the quiz?
If I give it on the quiz, it would just be one problem. But most likely not. I might ask you to do something for me or show me something instead of me giving it to you. Okay, so now we can actually get to the fun part, which is graphing. And we still have 20 minutes. Yay. Okay. I know you're so excited. I only have 4 graphing examples because once you've done one, you've done them all.
My graphs look really good. I still don't really understand the graphic from last. Are these the fun squiggle ones? Like,
No, that's polynomials. These are gonna look a lot like your radical graphs.
these are still just curves?
Yeah. So the first one I will be graphing is the function y equals log base 2 of x. When we start to graph these, the first thing we're going to have to do is we're going to have to turn it into an exponential because I can work with that a lot easier than I can work with this. So if I turn this into an exponential, Jimena, what is it going to be?
That's the first thing we did, right?
Yeah. Go back and look at the notes if you have to. That's okay. I don't mind that one bit. Hold on, Shane.
Okay, why is the one in front? Is that what it is?
Say that again.
The y.
Uh-huh.
Is that what it is?
Yeah, it's part of the equation. So that whole thing is my equation.
Not anymore.
Shush, it's still there. There we go. You're okay. This is hard. I know it's hard. So I don't mind if you take a minute to go back and look at the examples and really work your way through it. The base is a 2. Good. What's the exponent on that base? Just the y, yeah. And then it equals what, hun? X. Perfect. So that is the equation that I'm dealing with. 2 to the y equals x. There's really no way to simplify that to make it look nicer, and there's definitely no way to get y by itself. Well, there is, but we're not doing it. So what this means is that I need to think about the y's in order to get the x's. I know it's the opposite of everything we've ever done in our life, but that's the way we're going to do it. So I'm going to build my xy table. And we're going to pick our y's before we pick our x's. Yeah. So if we don't think about the fact that our exponent is a y, what naturally is something that I could easily take 2 to the power of? 1. I heard 1. So if my y is 1, what is my x going to be? 2. 2 to the 1 equals 2. So 2, 1 is 1 point I'm going to put on my graph.
How 2? What the hell?
Okay, so if y is 2 both, what is my x going to be? 4, because 2 squared is 4. So we're still thinking about it in the same way, just in the opposite order. We're finding our y or picking our y to find our x. I love that. Cadence, say that again. I should do y 0. What x does that give me if y is 0? 1. I have 3 points. I actually like to have 4. So I'm also going to pick a y value of -1. Because I want to. So what x does a -1 y value give me? 1/2. I have 4 points. I can now graph this.
Do we have to on that one?
Have 4 points?
No, I haven't.
You don't have to. It definitely gives you a better idea of what your graph is doing, but if you can graph it without it, that's okay too. So the really awesome thing is that majority of graphs are going to have a vertical asymptote and either curve up or curve down. And that will just depend on what our points look like. So let's graph it and I'll show you what I mean. So we're going to start with the first point, which is 2, 1. So I'm going to go ahead and put that one on here. My second point was 4, 2. My third point was 1, 0. And my fourth point was 1/2, -1. So as I'm looking at this, is my graph curving up from the bottom or down from the top? What does it look like here? Up from the bottom. I can clearly see that this is growing. And every logarithmic function that does not have a horizontal transformation is going to have a vertical asymptote at 0. Because there's no exponent that I could plug in for y that's going to give me a negative answer x. Nothing. Absolutely nothing. So we always have a vertical asymptote when it comes to logarithmic graphs. And we should definitely draw that on here. Are we all okay with how we graph that? Anybody super confused? It's okay if you are, but I would like to know. And then from here, I could go ahead and figure out my domain and my range. Just out of curiosity, what's the domain for this function? Brandon? What's the domain for that function?
No idea.
What's the domain for that function?
No clue.
Take a look at it and find out.
Negative infinity something.
The domain is the x values, right?
Wait.
I'll give you a second to wake up, get that mind going.
1/2 to positive infinity.
Actually, we would say 0 to positive infinity, but yes. Because my asymptote starts at 0, which means I'm going to get infinitely close to 0, even though I'm never actually going to touch it. Yes, ma'am.
How do you determine the thought like that?
It will always be at 0 unless I have some addition or subtraction happening in the exponent. And I'll show you an example where that would happen. Yeah, no worries there. No, you're good. Okay. Actually, it would be addition or subtraction with the x, but that's okay. What's our range then for this function? So that's my y values, up and down. Negative infinity to infinity. I have no indication that it's ever going to stop growing. It just might grow really, really slowly, and that's okay too. Yes, Madison.
So will the domain never be negative?
It will sometimes include a negative. It just depends on what's being added or subtracted to our x value. But for the most part, we pretty much avoid negatives. Only occasionally will it go in a little bit into that negative area.
Aren't you supposed to have the hard brackets on the domain? It's not supposed to go past
We would if we didn't have an asymptote here, which means I never actually hit 0 as an x value. I get really, really, really close, but I never actually get there. That was a great question. Anytime you have an asymptote, we always put a curvy bracket on that. And I did correct that on any of your guys' tests where you missed that part. I did correct the curvy bracket versus the hard bracket. Another example. Also, I know this is really boring, but let's try to stay awake. Nice. This is actually example D, if you wrote the notes. Which is why I'm picking it.
I looked away for 1 minute and
I did this. Yeah, I know.
would this be an example where the domain and range is?
Yes. Well, the domain, the range is always a negative infinity to infinity. Yeah. So I should note on an exponential function, your domain doesn't change, but your range does. On a logarithmic function, your range doesn't change, but your domain does. So they're kind of opposites. Okay, so the first thing I want to do here is I want to move some things around to make it easier to rewrite this as an exponential problem. So as of now, that -1 or that -1 on the end prevents me from rewriting this as an exponential problem. So I need to move that so it's grouped over with my y. That's the first thing you need to do. We only move something that's not grouped with our x. So this then becomes y plus 1 equals log base 1/4 of x plus 2. And now I can go ahead and rewrite this as an exponential problem. Patty, what's this going to be? I'll give you a second. That's okay.
I have an idea.
You have the power and the equals mixed. As the power, yep. And then equals? Perfect. So this is the same as 1/4 to the power of y plus 1, which equals x plus 2. Are we all okay with that? That one was a hard one. It's very difficult when we have letters and numbers and they're going in several different places. Anybody have a question on that one? Okay, so now I get the super fun job of picking y values and then finding the x value associated with it. So this one again is a little bit different because I don't just have a y in my exponent, I have a y plus a number. So I need to take that into account when I'm picking my respective y values.
-2.
Oh, I'm hearing lots of them. I'm going to go with -1 first. Why did you pick a y value of -1? It will turn into a 0, and I know 1/4 to 0 power is equal to what? 1. So I'm still picking ones that are really, really, really convenient. I also heard -2. I don't know who said it. Was it Brandon? Why would you pick -2?
Because it'll
So when I pick a y value of -2, what does my exponent become? And 1/4 to the -1 power becomes what? 4. Because it takes 1/4 and it flips it over.
Wait,
Are we all okay with that one?
I missed something. Why is it? Why? Because it's x plus 2 on the right side. Weren't you?
What did we miss? We forgot to add the 2. Again, this I see happen all the time. So my x value isn't 1 on the first one, it's 3 because I got 1 and then I added 2 to it. I was. And then I was going to see why it messed up our graph. And then I got 4 when I plugged in -2, and then I added 2 to it, and I got 6.
Wait,
Okay, I have another question. Why are you adding it instead of subtracting it? Would you subtract the 2 from that side to make it x
I'm
equals?
not having this on the notes.
No, I'm adding the 2 over here. That's what I wanted.
Yeah, something's not right.
Oh my gosh. Hold on.
Because I had 2, -2. But I don't know how you got that. So.
Yeah, I'm crazy. It's
-1,
fine.
-1.
We're going to start this one over.
So 1 minus 2.
It will be -2. Brandon was correct. I've been doing math too long today. So when I plugged in -1, I got 0. 4 to the 0 is 1, right? Then when I subtract this 2 over to get my x value, 1 minus 2 makes it -1.
I'm stuck.
What? Can you go do it again?
Okay, this is the same. As that. So that's what I'm doing now. When I plugged in -1, I got 0. 1/4 to the 0 is 1. Minus 2 gives me an x value of -1. I did the opposite. When we plug in -2, I get a y value of -2 plus 1 is -1, which flips my 1/4 to become a 4. And then 4 minus 2 becomes 2. I apologize for that. That was all me. That's 2 points. I need 4. So I need 2 more. Anybody else have a convenient
1.
x value I could plug in? We could do 1. That's fine. It's going to be super ugly, but we could do it.
I like
2.
Oh, I heard 0. Who said 0?
I said 0.
Okay, let's go 0. I like that. If I plug in 0 for y, 0 plus 1 is 1. 1/4 to the 1 power is 1/4. What's 1/4 minus 2?
I'm
One
not
and
sure.
3/4.
Well, that's 1/4 minus 8/4, because that's what 2 is equal to, which gives me -7/4. So we're actually going to stick it out with these 3 because we're almost out of time. And we're just going to graph these 3 and then approximate the rest of our graph from that. You're perfectly capable of graphing this with 3 points. I just prefer 4 for accuracy.
So do we have to have 4 on the homework?
On your homework, you will have to have 4, but none of them I don't believe are as crazy as that one. So the first thing I would like to note is that I actually did have a horizontal shift here, which means that my vertical asymptote is no longer at 0. It has moved. That horizontal shift came from that little portion right there. So because I added 2 to my x value, my vertical asymptote moved 2 in the negative direction, so to the left. Remember, horizontal behaves the opposite of what we think it should. So because this was a +2, I moved that direction too. So my vertical asymptote is at -2, which tells me that when I'm graphing this, I can't have anything that goes to the left of that dotted line. That's the easiest way to determine where your asymptote exists, and it should always be the first thing you put on your graph. If there's nothing added or subtracted to your x, it's a 0. Yeah. We only move it if something was put in there.
So we couldn't plug a number in that would make it under -2.
Correct.
Okay.
Correct. There's no possible way.
How do you spell that?
How do I spell it?
That's not how I thought it
Asymptote.
was.
Spellable.
Yeah, that's okay. As long as you don't sound it out like a cuss word, I'm fine. You will do that, believe it or not.
Have you ever had someone misspell like that?
I've had somebody say it in class. Okay, so now we're just going to go ahead and graph the points that I was given, and then we will be finished. So the first one I'm going to put down is -1, -1. The second point is going to be 2, -2. Based off of these 2 points, I'm going to assume it's coming from the top and curving to the left. And then the third point I'm going to put down is -7/4, 0. So that's -1 3/4. So that's going to be about here. I have my 3 points. I can go ahead and I can graph this. And we just draw a line that goes right along the asymptote and then follows our points. What would be the domain for this function?
-2.
-2 to infinity with curly brackets because it has an asymptote at -2. What would be my range? Flipped. -infinity to positive infinity. We always list the smaller number
Where
first.
did the curly brackets come from?
We don't have curly brackets.
You just said curly brackets.
I thought I said curvy.
Oh.
I thought I said curvy brackets. I'm sorry. No, curvy brackets. Curly brackets for sets of solutions. Oh my goodness. Okay. I promise that this is correct in the notes. I don't know why I messed it up here, and I'm so sorry for that. But your homework is all over graphing. I don't believe any are as crazy as this one, so you should be fine. I do ask that you also tell me the domain and the range of each function. I do want you to practice doing that some more. There are 5 questions. It is due tomorrow.